Today we want to begin exploring differential equations. Differential equations are one of the most useful topics in mathematics. For instance, we can use differential equations to model population growth. We can use it to model the decay of radioactivity for something that has nuclear radiation coming from it. We can even use it to model how a cup of coffee cools. And going a step further, if you look in the news at all of the modeling for the coronavirus, that's all using differential equations. So let's start with some easier cases and begin exploring differential equations. Okay, so I've mentioned some of the things differential equations are useful for, but I haven't yet told you what a differential equation is. So you may want to know, what is a differential equation? The definition is quite serious. It's quite simple, not serious. It is an equation that has derivatives in it. Okay, so to differentiate is to take the derivative. So a differential equation is simply an equation that contains derivatives, all right? And by the way, just so you know the lingo, when you get into college and somebody says they're taking Diff Eq, it means they're taking a differential equations class. It's just kind of the cool way to say it. So you'll know that you're in when you're talking to your friends about your Diff Eq class. So anyhow, back to the subject at hand. Let's look at a few examples of differential equations. In fact, the ones that are useful. Let's look at unrestricted population growth. This might be governed by an equation like dp dt is equal to 0.01 p, all right, where p equals the population, and let's say t equals the time, let's just say in years. Put that. Usually when we're talking about population growth for people anyway, we would probably be talking about how it grows over years. If you're talking about the population growth of, I don't know, something like mold, you could think of the spores as growing, then you might be talking about it in hours or something else. But let's talk about it in terms of years and figure out the meaning of this formula, all right? So this formula has a derivative in it. So it is a differential equation. Well, what this is saying is the rate of change of the population depends on what the population is. If p were 0, you would get a rate of change of 0. If there are no people, there will be no population growth. Whereas if p were 10 million, you see the dp dt would be bigger. Okay, so p is the current population. So if you have 1 million people, you're more likely to have more babies than if you had, say, 1,000 people. So the rate at which the population is growing depends on the population itself. Now notice we said unrestricted population growth. This means there is no lack of resources. In the real world, once the population gets to a certain size, the limited resources usually cause the population not to grow as quickly. So this is unrestricted population growth. Now what does the 0.01 mean? Okay, so this is a coefficient or a constant. This is the growth rate. Okay, we're going to take the population and multiply by 0.01, which would be 1%. Okay, now notice that's how much the population grows. So dp dt, let's say if p were let's say 100,000, then 0.01 times p would be 1,000. So if you had a population of 100,000, your dp dt, your growth rate, would be 1,000. You have 1,000 more people the next year. Okay. Now, what would happen though is the next year, so by year 2, you have 101,000 people. So the growth to year 3 will be slightly bigger because you had more people in the population after year 2. And so this will lead to a rate of growth that gets ever bigger, which we know as exponential growth. Right? We'll see in a couple of days why that actually is exponential growth. All right, let's look at another model. Let's look at nuclear decay. All right, so if you have a few grams of an actively radioactive substance, the radioactive portion of it will decay away. It doesn't disappear, it turns into something else. It's not radioactive usually. But let's just say that A equals the amount of radioactive material, and we'll say it's in grams. All right, and T will be the time. Now this depends on what kind of radioactive material you're talking about. It could be, let's just assume it's in years for this example, but some things decay very, very quickly. So you might talk about it in minutes or even seconds. So it depends on what we're looking at. But we'll look at this as time in years to give this some meaning. All right, and we want to find, let me write a differential equation, dA dt equals negative 0.01 times A, right? So there's in the last case with population growth, it was positive 0.01 times P. This is negative 0.01 times A. So what is this going to do? It's going to do something very similar to the last case. The rate of change in radioactive material depends on the amount of radioactive material. I'll just say amount of material. Okay. Now, this time, though, you'll notice we have this negative 0.01. So dA dt is negative. Okay, so we're losing radioactive material as time goes on. This says we're losing 1% of the existing amount each time period. Okay, so let's say that at time 0, you had 10 grams for A. Then at time 1, we've lost 1% of that. Let's just make it easier. Let's say 100 grams. Then we have 99 grams left. Okay. Now at time 2, the answer will be less than 98. Because we're not losing 1 gram. I'm sorry, we're going to have more than 98 because we don't keep losing 1 gram. When you have 100 grams, 1% of that will be 1, and so you would lose 1 gram. But then when you get to 99 grams, 1% of that is 0.99. So you don't lose a whole gram. You end up with 98. Let me just actually write that in. It would be 98.01. Okay. So each step along the way, you lose a little bit less. And so this leads to exponential decay, which you've hopefully learned about before. And we'll determine that specifically on a later day and see why that is exponential decay. So it will drop more quickly at first when there's a lot of radioactive material around. As the amount of radioactive material dies off, it will die off at a slower rate, which is good because radioactive material, it emits dangerous particles as it decays. So as you have less of it, it decays more slowly, which means it's less radioactive and less dangerous to be around. All right, now let's look at one of my favorite examples. Let's look at cooling a cup of coffee. This is a little bit like radioactive decay because, not because coffee is bad for you, but because we are going to have a negative rate if we start with a warm cup of coffee. All right. So let's let capital T equal the temperature in degrees Celsius. All right. Um, we'll let, and little t will equal the time, but this time it wouldn't make sense to talk about years. Clearly, I'm not going to have my coffee sitting around for years. Let's look at the time in minutes. You could do it in seconds, but we'll do it in minutes here. All right. So I'm going to write a differential equation. And it's going to look more like this. Okay. So I think you can understand the first part is the rate of cooling. It's actually the rate of temperature change. But because we have a negative in front of the 0.05, we know that this is going to be a negative rate of change. Okay, and then if you look at this, this is, once again, this is about 5% loss. Okay, each minute that passes, we're going to have about a 5% loss in something. Okay, but what that something is a little more complicated than the case we had just looked at with radioactive decay. What's decaying is not the temperature, but the difference between the temperature and this number right here, which is room temperature. Once the coffee cools to room temperature, we don't expect it to cool any further. So it's the difference between the temperature at the moment and room temperature. So initially, if you started with T equaling 100, if you had boiling water, all right, or boiling coffee, then T minus 20 would be 80. So what's decaying is the 80-degree temperature difference. Later on, when the temperature has dropped to, let's say, 60, then T minus 20 is only 40. So we have half the temperature difference. So the coffee cools at half the rate when there's half the temperature difference. We're losing 5% of the temperature difference between the current temperature and room temperature each minute. So that's what this model is saying. So what would happen is if we were to graph this out, here's 0. Let's just say we started up here at say 100. We would not expect our coffee to cool like that. That would be a linear decay, and it would freeze at the end of that. All right. We expect there to be some kind of asymptote, and the asymptote would be right about here. This is the 20-degree mark right about there. And so what we would see from this model is that we're cooling rapidly at first, but we cool less and less rapidly as time goes on. I don't have a time scale in here, but here's the time in minutes. And depending on how much insulation is in the cup of coffee, or the coffee cup, I should say, hopefully not in the cup of coffee, we would change how fast that might drop off, but no matter what, it's not going to drop below the room temperature. So we would see a curve that looks something like that. So these are just some quick examples that show the usefulness of differential equations. Now let's get into some of the nuts and bolts.